Welcome students to part 2 on trigonometric equations. Today we're going to be looking at trigonometric equations which have alternate inputs, like instead of sine theta is equal to something, see what happens when there's like a 2 theta or a theta over 2 or 3 theta or something, and show you how we can use a simple substitution to make these a lot simpler. So let's start off with a pretty easy example. Let's say we had sine of 2 theta is equal to rad 2 over 2. One thing you could do is use a double angle identity, because sine 2 theta is equal to 2 times sine theta times cosine theta, if you are up to speed with all your different identities, which could work, but then that equation would be 2 times sine theta times cosine theta is equal to rad 2 over 2, which would be solvable, but would be a little bit more difficult to actually figure out. So what's actually nice is there's a simple substitution we can do, which will then basically turn this equation into sort of a normal basic trigonometric equation like the one that we looked at in part 1. We can do everything we learned how to do just when we're solving those in these, and then just figure out how to reverse the substitution at the end. So here's kind of the idea. Anytime we have anything besides a normal theta in our trig input, it's going to be harder to solve because we're now looking for 2 times an angle instead of just a normal angle. So the trick is to make the substitution whatever your input of your function, in this case 2 theta, and make that equal to something else. Some will do u or x or phi or whatever. I'll just use phi because it looks kind of like theta but just different. But basically I'm going to change my 2 theta input of my function to this phi. And now what will happen after we make the substitution, 2 theta is equal to phi, my equation will simply become sine of phi is equal to square root of 2 divided by 2. And like going back to our last topic, this we can now solve with a unit circle. So pulling up the unit circle here, where if we're trying to figure out what phi in this case would result in root 2 over 2. So remember, sine is defined to be the y-coordinate on the unit circle with respect to whatever angle you're at. So we're looking for, this is our given y-coordinate. We're looking what angle would produce a y-coordinate of root 2 over 2. That's essentially what this equation is asking, if an equation could talk. So anyways, we're looking for the theta values, which would give a y value of root 2 over 2. So we look for where is y root 2 over 2. So there would be one place, our y value is root 2 over 2. So the corresponding position would be pi over 4. So that, again, what that tells us based on trig function definitions is that sine of pi over 4 is equal to rad 2 over 2. And the secondary, just like last time, is over here, directly across to the left. So our secondary solution, where sine is root 2 over 2, would be 3 pi over 4. So we find our first two solutions using the unit circle. So we get that phi should be equal to pi over 4, the one on the right, and the secondary was phi should be equal to 3 pi over 4, the one on the left. And we generalize by adding any coterminal solution or adding 2 pi k to each of these, and that will make sure we take into account every potential solution. So essentially we solve this in the same way we solved those previous equations. I'm going to use this every solution form instead of just the interval 0 to 2 pi. The reason why this one is useful is because sometimes these double angle equations like this actually have more than 2 solutions over the unit circle, and if we don't take into account the plus 2 pi k, then we're going to lose some solutions if we try to find them all later on. So anyways, we generalize it by adding 2 pi k, and so of course we're trying to solve the original equation for theta, not for this new variable we created, phi. So we're not done yet, because anytime you're asked to solve an equation like this, you don't want to solve it in a different variable. So we want to know what theta is. So again, basically what we do next is back substitute. Our original substitution said that 2 theta is equal to phi. That was the trick we could use to quickly identify which angles would solve the equation. And then if we go back and change phi to 2 theta, which it originally was, then we could solve this particular equation for theta, and then we'll have those theta values we're looking for, the solution to the original equation. And so, as you might guess, to solve this equation for theta, all we need to do is divide both sides by 2. Since we have 2 times theta is equal to this stuff, we divide by 2, and that would get us to theta. So divide everything in here by 2. So we need to make sure to do every term divided by 2. So pi over 4 divided by 2 would make pi over 8. And then 2 pi k divided by 2 would just be pi k. So we get plus pi k. And this would be one of our solutions. And then over here, if we divide the secondary by 2 theta is equal to 3 pi over 4 plus 2 pi k, we divide everything in that equation by 2, we get theta is equal to, 3 pi over 4 divided by 2 would be 3 pi over 8. And 2 pi k divided by 2 would just be pi k. And so this would give us our sort of secondary solution adjusted. So what you might notice is it looks very similar to solving sine theta is equal to something. We get 2 sort of answers plus thing, but what sort of is altered with a double angle inside of our equation is that our answers actually are half of the normal angle solution. So the normal solutions to this type of equation would be pi over 4 and 3 pi over 4, but now they're half of that, so pi over 8 and 3 pi over 8. And so these would be all the solutions to the equations. If we're looking for all the ones on the unit circle, it would be those 2 pi over 8 and 3 pi over 8. But there's actually going to be a total of 4. Since our angle's been halved, there's actually going to be 4 more. And if you plug in 1 for k in each of these, you're going to find the other ones that are also in the unit circle. So for example, if we take this equation right here, and we plug in 1 for k, that's going to give us another one. So let me go ahead and do that. So I'm going to plug in 1 for k. That would be theta is equal to pi over 8 plus 2 pi times 1, because the 2 went away and we divided both sides by 2. So let me erase that plus. Let's get back to here. Plus pi times 1. So I'm plugging in 1 for k just to find. The reason being is this is also going to be on the unit circle, but this will give us pi over 8 plus, well, pi times 1 is just pi, so this would be a plus, but for some reason it's appearing as a minus. There we go. Plus pi times 1. Well, if we're going to add these pi over 8 plus pi, it's going to work just like adding a fraction 1/8 plus 1. We have to match denominator. Anytime you add any, when you're trying to add fractions, you have to have a matching denominator. So we could turn our pi over pi times 1, which is just pi over 1, multiply that by 8 on top and bottom. That would give us 8 pi over 8 as the fraction pi. Because remember, 8 pi divided by 8 would just be 1 pi. But anyways, we would have pi over 8 plus 8 pi over 8. And again, once we match our denominator, we add the numerator. Pi plus 8 pi would make 9 pi. Just like x plus 8x is 9x, pi plus 8 pi is 9 pi. And so this solution here, 9 pi over 8, would be also actually on the unit circle, because this angle is slightly bigger than 90 degrees, which, remember, 90 degrees is pi. So that one's also on the unit circle if we're looking for all the solutions on the unit circle. And then we could do the same for this one, for this equation right here. If we plugged in 1 for our k there, that would also give us another solution on the unit circle. So we would have theta is equal to 3 pi over 8. Again, it would be plus pi times 1 again, and that's going to be 8 pi over 8. So kind of the same thing. We'd add 8 pi over 8, and that would make a total of 11 pi divided by 8, which is also on the unit circle, that one. I think that one's also in quadrant 3, but you could look at what those are in degrees if you're trying to figure out exactly where those are. And so finally, essentially, to summarize, the 2 that I circled will be all the solutions, but if you're asked to find all the solutions in 0 to 2 pi, we would plug in 1 for k to find. So again, this would be unnecessary. All the stuff in green is unnecessary because those solutions are included in this generalized form, because every repeated solution would be already accounted for. But if we're looking for the specific ones, all you got to do is plug in k is equal to 1 in this case. to find all those other ones. Okay, so let's move on to another example. Let's do a half angle. Let's say we had cosine of theta over 2 is equal to, I don't know, let's say root 3 over 2. Let's do ones on the unit circle so that we don't have to use an inverse to calculate them. But again, same sort of trick. We could take our input of our function theta over 2 and again call that phi, make a simple substitution, and that way our equation would change from cosine theta over 2 to cosine phi is equal to root 3 over 2. And this, again, we can solve like the last tutorial by evaluating where's cosine rad 3 over 2. So pulling up my unit circle. Cosine, remember, is the x-coordinate. So our x-coordinate right there is where cosine is right there is where rad 3 over 2. So one solution to this would be phi is equal to pi over 6, because that would give us a cosine of root 3 over 2. And the other cosine, being root 3 over 2, is down there, which in the interval 0 to 2 pi would be 11 pi over 6. So we get these two as our solutions. So let me go ahead and write those down. So we would get phi is equal to pi over 6. And we get phi is equal to 11 pi over 6. And again, we could add 2 pi k to compensate for any other solution beyond just the unit circle with cosine. And from there, then we want, of course, to back substitute to find out our original theta. Because again, phi is not the answer to the given equation. The given equation is in theta. So what we would do would we would then back substitute in theta over 2 for phi. So theta over 2, since that is equal to phi, we just put that back in. And now to solve each of these for theta, we would just multiply both sides by 2 to cancel that division by 2. And so as we multiply both sides by 2, we would get on the left side, we get theta is equal to, so if we multiply this one by 2, we would have pi over 6 times 2 would make 2 pi over 6, or pi over 3, and 2 pi k times 2 would be 4 pi k. And then if we multiplied this one by 2, we would get 11 times 2 is 22 over 6, which would reduce down to 11 over 3. And then we could also multiply the 2 pi k by 2, which would be 4 pi k. So just to write out what I just said, we multiply that one by 2. We would get theta is equal to pi over 3 plus 4 pi k. And we multiply this one by 2, we would get theta is equal to 11 pi over 3 plus 4 pi k. And now this would be all the solutions to that equation, kind of in one little place. Again, k being any integer, and that would be all of them. So, it's not a big step beyond the first one. Really, the key is doing the correct substitution, making the substitution, solving it, resubstituting, and then doing whatever you need to do from there on out. And that'll give us all the solutions. And again, you can try, what I didn't do last time is showing you kind of checking our solutions here. So we could take, some of these solutions, like for example, when k is 0, we could take these bad boys and make sure that these values actually work in the equation. So let's actually do that. That's going to be a good exercise. Anytime you're dealing with an equation, it's always good to check your solution to make sure that it does indeed work in the original equation. I just wanted to do an example with a double angle like this. So let me just erase this stuff really quickly. It's kind of slow. Almost done. I didn't want to erase the whole page. So, okay, going back to the original equation. So if we plug those two values that I boxed in for our theta, let's make sure that it works out. Because, of course, when we're solving an equation, we want to make sure that it does work. So let's plug them in. So we get cosine Well, we got that theta was all these values, pi over 3 plus 4 pi k, 11 pi over 3 plus 4 pi k. But let's just do k is equal to 0. You could plug in any k you want, and all those should also work. But if we plug in pi over 3 into the equation, so we'd have pi over 3 over 2. And so, of course, this should be true if our solution is indeed right. So pi divided by 3 divided by 2 again, you could use the flip and multiply rule, but if you divide it twice, that would just make pi over 6. And cosine pi over 6 is kind of like, well, what did we do to begin with? We figured out where cosine was root 3 over 2, and that's pi over 6. But again, going back to our unit circle, if we plug in pi over 6 into cosine, what we get is our x-coordinate root 3 over 2. So it checks out. And the same would be if you plug in 11 pi over 3. What would happen is if you plugged in cosine of 11 pi over 3, and that would all be divided by 2, because we have cosine theta over 2 as our original equation. When we plug that in, that would give us cosine of 11 pi over 6. And of course, if we evaluate cosine of 11 pi over 6 on our unit circle, 11 pi over 6, it was the original position we were looking at, gives us a cosine of rad 3 over 2. So essentially, we already solved this earlier when we were doing that substitution. But the substitution is just a clever way to figure out how does our dividing by 2, multiplying by 2 mess with our final result. And so that checks out and gives rad 3 over 2 as well. So both of those solutions check out, and you can also try plugging in those other k values into, k is 1, k is 2, those other ones we figured out just like from before to make sure that those are work. But those are the only two that are on the unit circle in this case. And actually, in this case, 11 pi over 3 isn't even on the unit circle. Well, in the normal 0 to 2 pi range, it is, every angle is on the unit circle, but in the normal 0 to 2 pi, there's only one solution to this equation, pi over 3. The 11 pi over 3 actually exceeds 2 pi, so not on there. Anyways, let's do one last example. So let's say we throw a lot of this stuff together. Let's say we had a tangent of, let's say, 3 theta plus 1, and we want to figure out when that's equal to 0. I don't know, whatever. Similarly to what we did before, we could do a substitution to take our entire input of our function, call that phi. Again, you can use whatever letter you want, but just using phi because that's how I do it. But some other books might use a or u or x or whatever, but we'll call phi 3 theta plus 1. And so in my new equation, after I make that substitution, will be tangent of phi is equal to 0. We solve this like a normal trig equation. Again, this one I chose so I could do it with the unit circle. But whereas tangent 0, remember tangent is y over x. So we're looking for our ratio of y to x to be 0. So at the original position 0, our ratio y to x would be 0 divided by 1. So 0 is a solution to this, as is actually also pi, because ratio 0 to negative 1 would also be 0. And remember, at pi over 2 and 3 pi over 2, tangent's undefined. That ratio is not 0. It's actually negative 1 to 0 or 1 to 0, which is undefined. So these two don't work for this equation, but these two, 0 and 180, do work as our two solutions to the tangent. So we get that our phi would have to be 0 radians, or also degrees, or it would be pi radians, or 180 degrees. And so those are our two solutions. But if you remember about tangent, you actually only need to find the first solution, and you could add pi k to that to generalize it, or you could add 2 pi k to both, either way. But I like to just find one solution, add pi k, that gives you all of them. So then we would get the solution theta is equal to 0 plus pi k, or just, phi is equal to 0 plus pi k, or just phi is equal to pi times k. And again, last step would then be to back substitute. So we would change phi into what our original substitution was, which was 3 theta plus 1. So 3 theta plus 1 is pi k. And then we'd solve this for theta, just as we would a normal equation. So we would subtract 1 from both sides. So 3 theta would be pi k minus 1. And then we would divide by 3. Theta would be equal to pi k over 3 minus 1/3, and then this will be all of our solutions to this particular equation. And so, again, you could check it out, make sure it works. But notice that if you plug in 0 for k, you would get negative 1/3. If you plug back in that negative 1/3 to the original, you'd have negative 1/3 times 3, which is negative 1 plus 1. You get tangent of 0, which is indeed 0. And again, you can verify with your calculator as you change k to 1, 2, 3. All those would also be solutions to the original equation. And so that's kind of the end result. So if I could summarize everything quickly, basically take the input of your function, make a substitution, solve it as if it was just a simple trig equation. Remember, you can watch my part 1 video on all that if that's what's tripping you up. And then after you solve that, this particular easier equation for phi, back substitute to whatever your original substitution was, isolate theta in there, and that will give you your original solution you're looking for, the theta that will work in the original equation. Thanks for watching. See you guys around.